Thank everyone for sticking around, and it's been a tough day. This hopefully give you a little bit different perspective, an engineer's perspective on hydrogeology. So it'll be interesting. At least see how we visualize, at least how I visualize it. But I want to start off by pointing out my opening slide here. Treatment. It's a train. There's several reasons I started out with having a train on this slide. Treatment train is what we all think about when we think combined remedies. Railroads pay the bills, and a mother goose analogy wouldn't work too well on an opening slide. Also, it's a proven analogy that's drilled into us from early ages. Each car is a separate unit process. It is strung together to combine discrete actions of a successful remedy. It efficiently couples a technology and its applicability, much in the way that Jeremy explained in his presentation. And it allows you to plan for some predictable changes. Those changes allow you to maintain those optimal efficiencies throughout the project. And those efficiencies can be measured in time, cost, and other sustainable criteria. So this is basically what I'm going to talk about, a little bit of a roadmap for you. I'll go into a little bit of background about what's important with combined remedies, at least in the framework that I'm talking about them. And that'll be talking a little bit about continuing sources and rebound. Touch upon the obstacles to some of these solutions that Jim mentioned this morning. And then I'll get into some case studies. And if there's time at the end, we might talk a little bit about a sustainability assessment that I threw in there because I submitted this paper to the SUSREM folks up in Montreal. Actually, before I go further, I want to point out the first part, the continuing source. And this antique sign here, train sign, just reinforces, I don't need to tell this crowd that you need to remove NAPL before you begin remediation in the dissolve phase. But just in case you're questioning it, the theoretical oxygen demand of diesel is equal to 300,000 times an equivalent volume in DO saturated groundwater. Think about that. 300,000 times. But that's enough talking about, removing NAPL. I think everybody in this audience gets that. To better understand rebound, we need to talk about where the mass is distributed. So it's separate phase, we're done talking about it. Also can be sorbed to sediment or dissolved in groundwater. This, basically that's where the contaminant mass is located. And how it's distributed between those is all site-specific type criteria, contaminant-specific and the matrix. Let's take a closer look at an aquifer, and you see the distribution of contaminants that show being sorbed and dissolved in groundwater, represented by the blue and green circles. Let's follow what happens as we inject an amendment, a remedial amendment, and what happens with treatment as it progresses. So immediately following the injection, you get great distribution, hopefully, if you planned your project the right way. And as soon as the amendment is depleted, think of a chemical oxidant, a quick burn, or even a microbial stimulant. Once they're depleted, you typically see great attenuation in the dissolve phase. And here's an example of what you might see from a lab report. This is actually an actual lab report from a site in Switzerland, a degreaser, where immediately following ISCO application, we saw a great concentration decrease, 3,000 to 80, and a similar isotopic fractionation that you would expect with that type of concentration decrease. But as I think we all know, that's not the end of the story. After chemical oxidation or any biological process, they're more efficient in the aqueous phase. So after a period of time, you have equilibrium partitioning, and you get more contaminants moving from the soil sorb phase to the aqueous phase, causing a rebound. And here's what that lab report was, same site, results look like following rebound a couple months after the initial sample was collected. You saw a rebound back up to 600, and you also saw isotopic rebound, indicating that you did not get complete treatment. There's another type of rebound that we can see, another mechanism causing rebound that has been talked about a lot this morning and this afternoon. And that has to do with preferential flow paths. You know, when you inject, the amendment is going to be restricted to advective transport corridors. And again, after the amendment is used up, it allows for back diffusion of, from less permeable areas into that high flow area. And when you sample that high flow area, or collect a groundwater sample, you see rebound, you see additional contaminant mass enter there. Isotopically, I wanted to point this slide out because it kind of cuts through a lot of confusion. What happens when you have baseline conditions up here? Your C13 to C12 ratio in the aqueous phase is in equilibrium with the C13 to C12 in the sorb phase. Following treatment, you're preferentially removing carbon that has C13 in it because it's, you're preferentially removing the carbon that has C12, chemical bonds comprised of C12. The C13 is not as reactive to C12, and it will accumulate in residual mass that you measure. So following treatment, immediately following treatment, you have great isotopic fractionation with much, much more C13 to C12 ratio in the aqueous phase than in the sorb phase. And then just thereafter, you get partitioning back and forth in the soil to groundwater and back diffusion from totally untreated sources coming back in and mixing with your treated groundwater, explaining why you get rebound, both concentration and isotopic rebound. So the conclusions we can make about mass distribution is remove the NAPL first. I think we all know that. Nearly every site has characteristics that promote rebound. I think that was hammered home this morning. There are very few sandboxes out there. I have never bumped into one. You also get diminishing turns when you stick with one technology, like ISCO, as shown in that isotopic and concentration rebound. So this justifies combining remedies to achieve a more efficient cleanup. So that means we also have to consider other technologies. This is probably a good place for me to pause, because it is the pinnacle of my public speaking career. You know, I'm here at the Beckman Center with a great panel of speakers, and just used a schoolhouse rock analogy and concluded it with a modifying conjunction. That's my English teacher would be so she'd be in disbelief, but I was a science guy. Oh well, we'll move on from there. So some of the obstacles that we have to implementing combined remedies are some real, some perceived. It's highly technical. You need schedule flexibility, or even flexibility in what you want to do after the first action. And it's difficult to justify to stakeholders, or it can be. And I find the owners are probably the most difficult to explain these justifications to, because they don't know if the costs are additive or cumulative. The only thing that's more expensive than one remedy is two remedies. They have that philosophy. They don't know better. It's our job to explain it to them. They're not technical people. Regulators are a bit more technical than our clients, typically, and you can usually explain and justify the rationale for using combined remedies. But one of the solutions that I want to promote here, or talk about for the balance of this talk, is maybe we don't need to think as sequential treatment trains. Maybe we can combine remedies in multifunctional, multi-component amendments that stimulate many degradation pathways. But if you really need to use the treatment train analogy, think of it as multiple cars or containers per car, or running on parallel tracks. So I'm going to present 4 different case studies here. And they're all with about using stimulating multiple chemistry and microbiology degradation pathways. So I'm not talking about physical combined with microbiological or chemical. This is strictly chem bio. It's all in a single amendment, so one injection. And all of them are intended to increase the treatment lifespan and to maximize mass removal and manage rebound. I've backed a whole bunch of these case studies with molecular biological tools. I like Jack, love molecular biological tools and use them in all of my sites. Thanks, Jack. And I purposefully did not mention amendment vendors' names. Talk to your favorite amendment vendor. If you want to know how to use they can make suggestions to how they can advise you on using their products in these formulations. If you don't have a favorite amendment vendor, let me know. I'm happy to introduce you to some of mine. Many of them are in the room today. So we're going to talk about sequencing a couple of these. One of the sites we're going to talk about is about stimulating abiotic and biotic oxidation. So that's basically using electron acceptors to activate radicals. And the other is iron-based treatment, where I'm using abiotic reduction combined with bioreduction, and even a case where I'm combining it with aerobic oxidation. All of these case studies in the number 2 here involve iron, either zero-valent iron or reduced iron metals. I want to point out that they're very complementary, bio and reduction, abiotic reduction. Now, I know a lot of people are probably stuck on the 1990s and early 2000s philosophy that you have to be careful about your loading of competing electron acceptors. That's been largely disproven. Kevin Finneran came out with a paper in 2011 that showed, no, you can get DHC growing at great numbers in an iron-reducing environment or predominantly iron-reducing environment. Kevin's a big fan of stoichiometric dosing, and I am too, and I encourage people to take a look at this if they're still disbelievers. Reduced using iron and bio, using dihalococoides, that's DHC, reduces inhibition and allows bio to occur at a better rate and better circumstances than if it were used, bio were done independently. There's a few different mechanisms why this happens. Sulfides a known inhibitor. If you have an iron-based system, you can have ferrous iron generated when you add an electron donor. That will precipitate out the sulfide and reduce the dihalococoides inhibition to sulfide. You get abiotic treatment on the iron surface of 111-TCA, which is also an inhibitor of dihalococoides. Iron reducers supply B12. That's fairly new stuff. I refer everyone to Frank Loeffler's recent work about cobalamins, and DHC cannot produce cobalamins. They rely upon interspecies transfer. Geobacter transfers can make B12 and can transfer it to DHC. Geobacter is an iron reducer. Also, iron, not listed here, but iron, all zero-valent iron oxidation increases pH. So you can move a mildly acidic aquifer into a more favorable pH range for dihalococoides by using zero-valent iron. On the other hand, some reduced minerals are very difficult, have a difficult time with dichloroethene, where bio does not. So DCE can be very problematic if you have, if you're using certain reduced iron minerals, especially like iron sulfides. So all of these are complementary. Iron and bioremediation are complementary technologies. The iron generally, because it's surface bound or precipitates out fairly quickly, is positionally locked soon after delivery, whereas electron donors can move around endogenously and diffuse in a little bit more, so you get a greater radius of influence for a single application of just iron alone. The combined approach lowers redox potentials. Adding an electron donor minimizes surface pacification of iron surfaces. extends the longevity of treatment. The irons have a lot more electrons stored into it than a fermentable electron donor that you're going to add in there, organic electron donor. And all of these combined help manage rebound. They extend the longevity of treatment. There it goes, right? I'm getting to the case studies. So what I did was I just have my desk here, and I'll show you the first site here is in Ontario. This was a site where I added, it was contaminated with TCE and daughter products, and I decided to go abiotic with abiotic iron, ZVI, reduction, and biodegradation using dihelicoides. And so the formulation was ZVI, a fermentable donor. I actually have written on here bioaugment, but we did not augment here because we had a good concentration of DHC naturally occurring. So here is the figure showing the location of the plume, and we started out with 14,000 micrograms per liter of TCE and reduced it to 7, all the way, and as of last November, it was at 7.6 micrograms per liter of vinyl chloride was the highest detection that we had at the site. There was no other detections of any other compound. So that's a 99.9% treatment efficiency, and data that we just got last week showed that we now we're in compliance. We're 2.0, below 2.0 in all the wells of vinyl chloride, so we're at 100% cleanup here. So wanted to show you here that concentration decreases from when we applied the amendment. You're fairly regular. You can't really see that, so let's take a look at a graph. And you see it's a pretty steady decrease in concentrations from the injection amendment all the way to, this is the November data, is the last data point graph there. What I really want to point out here is the blue line here is 1,1-DCE, and the lighter blue line is vinyl chloride. So we just added ZVI, and you expect to see more parallel degradation patterns, but we see a classic biodegradation pattern right here, where you see a decrease in the dichloroethane and an increase in the vinyl chloride. But later on, we have parallel lines all the way down. So it looks like this is a mixed biotic-abiotic situation. And here's the microbial data here. What's that number? It's 8 times 10 to the 8th. That's in cells per liter. So there's plenty of DHC. It's above that threshold that was mentioned earlier by an order of magnitude. So one way to figure out whether you have abiotic or biotic is to look at this term called FAbiotic. FAbiotic takes you, to calculate it, you take the sum of your VOCs, including ethane, ethene, at time 1, you subtract, and this is all in molar basis, subtract the same from time 2 and divide by time 1. The results that we ended up getting down here is that 3 wells, the FAbiotic term was approaching 0, indicating biotic, primary mechanism. 3 wells were approaching 1, indicating abiotic, and we had 2 that were mixed, with FAbiotic terms pretty much dead center in the middle. The next study is a site in Missouri. The contamination here is TCE and TCA and its daughter products. Here, we added sulfate, ferrous iron, a fermentable donor, and I also bioaugmented. Now, this is quite the stew. And let me explain what the thoughts were here. So we were trying to create iron sulfides in situ. So the formula for doing that is add some sulfate and electron donor, you get sulfide produced. Add some iron, or either naturally occurring or added, and you get ferrous iron produced. They'll combine, precipitate out, form iron sulfides. There's a little bit more to that, but that's the basic formula. These iron sulfides coat the particles in situ and are reactive, similar in a way that ZVI is reactive. This slide's here to point out that this is a bedrock application. It's in limestone, and I think this is the first bedrock application of biogeochemical transformation. Since done a couple others. So after, we've got great concentration decreases. You can see here, everything's down. I think we on average had 66% molar concentrations. I picked a good well to show you guys. Actually, these are individual wells. I shouldn't say that. So each of these wells is plotted here, total VOCs on a micromolar basis. The average molar mass removal was 66%. And the Abiotic, the interesting thing here is to look at the Abiotic trends. Remember, that's the figuring out whether you have biotic or abiotic reactions occurring. The factor was 0.19 after 1 year. That's a biosignature. After 2 years, it's up to a mixed signature. This is the sort of reactivity that you would expect as your donor depletes and your dihalocoides can no longer survive. Then you have the stored capacity for treatment in the iron sulfides becoming more prevalent as far as managing the site. This is how to manage rebound by using something that lasts a lot longer than microbes possibly could. Third site. This is one of my favorite. And it's actually fairly complicated. I'm going to go through it pretty quickly here, but this work has been published in Remediation last summer or the summer before. All right, so this is abiotic reduction and aerobic bio. So we added ZVI and a fermentable donor. Here's the plume. DO was always measured 0 in all of these wells. ORP negative, trichlorobenzenes are the contaminants. There's some dyes and a little bit of chlorobenzene here, no benzene. Read a paper that out of Germany that basically said you can anaerobically oxidize chlorobenzenes. That means using an electron acceptor that is not oxygen. So in their study, they did stable isotope probing and to PLFA, the phosphofatty lipid membranes, and they claimed anaerobic oxidation using sulfate. So I'd say, hey, this is great. I know I can make trichlorobenzenes, dichlorobenzenes reduced to chlorobenzene pretty easily. That was shown in the paper right before me. So if I just have to add a little bit of sulfate as an electron acceptor to deal with the chlorobenzenes, that would be awesome. But, I'm just like Jack. I'm not just going to buy this paper here. I proved it in the field. So I did a in situ microcosm study where I did the same study that they did in Germany, but I traced it back to the DNA of the microbes that were attenuating. So what I ended up finding out was that we did get heavy microbes where their DNA was abundant in C13, and the microbes were Acinetobacter and Trichococcus. Now this, and the microbiologists are perking up here, I can see it in their eyes. These are obligate aerobes. Now, this is an environment where the DO of the groundwater has always been measured 0 in the wells. We just added ZVI, we just added an electron donor, but I have an obligate aerobe responsible for chlorobenzene degradation. So I added C13 enriched chlorobenzene to my in situ microcosm. The C13 ended up in those bugs. So, it comes to find out that microaphilic isn't a new deal. It's been around forever. The concept's been around forever. Gossett postulated that, this is probably a reason why vinyl chloride doesn't accumulate sometimes, is that you have microaphilic conditions, and you can get degradation along the aerobic pathway, even in an anaerobic environment. This is probably highly site-specific. I stumbled across it. It was dumb luck. But it's great for the client because we've implemented this at the site and well on our way to treatment. I hedged also. I put in sparge points just in case I had to turn them on. All right. And last site, the one in Florida is the simplest one. Here's the footprint of the plume. Here's the footprint of the plume after about 1 year. Turns out there was a little bit of napple inside between the tanks here, which straddled the water table. They got hung up. Always remove napple or you're not going to get dissolved phase. But I should back up a little bit and let you know what we put in here. This was a site where we used persulfate activated with calcium peroxide. That's an oxygen-releasing compound. So you get 3 different mechanisms of degradation with that particular formulation. You get direct chemical oxidation by the persulfate radical. Then you have residual DO coming off the calcium peroxide as it dissolves. that stimulates aerobic biodegradation. And then you have the degradation product of persulfate. The sulfate acts as an anaerobic oxidizer, anaerobic terminal electron acceptor. And you can see what happens here initially. We have, after concentration, baseline samples here. We have great concentration reductions. And we see a great fractionation immediately following concentration reduction and fractionation from literature values. This test wasn't offered back when we did baseline sampling. So if you go off literature values, the isotopic signature of benzene and MTBE should be in the minus 30-ish range. So that's a significant fractionation showing that we got direct chemical oxidation immediately following degradation. Then we got some rebound and then continued degradation. And not only did the concentrations go 84, 930, 368, but we saw the same deal in the fractionation. So highly fractionated, have an isotopic rebound, and then you started to see fractionation again. Down to 1 minute, I'm going to make it. Using Ryan's theory. There's an explanation for this. Use the microbiological data to figure out what are the mechanisms that are causing this. And baseline data, I did DNA analysis of the microbes and found out that they were loaded with the capability of producing oxygenase genes. Later on, I did, towards the end of this project, as we were in the aerobic phase, I ran the RNA, so the expression of that DNA that's measured here. So you can see that we're producing oxygenase enzymes as would be predicted by what we were trying to do. The calcium peroxide dissolving oxygen, giving DO to the microbes, they're producing these oxygenase genes. And then we got degradation here on the other slide, but there's no oxygenase genes. This is anaerobic oxidation. There were very few soothase targets back when I was running these, so there's no data. And the only reason, this is a sustainability analysis saying why it's so good to do treatment trains versus discrete applications. The only really cool thing here is this image. I love this. So I'll conclude on that, and thank you. Thanks for sticking it out.